Yes, ma'am.
Okay. In today's session also we are going to continue with the shift register. In earlier shift session, we discussed about parallel in parallel out shift register. Okay, so that means data will come in parallelly and it will go out parallelly. Okay, so for that we have written the VHDL code and after that we have simulated it also. So in that we found that whatever we are, what is the input to the parallel input. So same will be available at parallel out. Okay, so that means output terminals. So that we discussed in a earlier session. Now in today's session, we are going to discuss about serial in parallel out shift register. So can anybody tell me what is mean by parallel serial in parallel out shift register?
The data is shifted the serially and we get the output parallelly means after one flip flop we get the output.
After one.
Af- After every one flip flop we get the outputs mean that is a parallel output.
So here, in a serial and parallel out shift register, data is input is data input that is come in a serial way. Okay, so that means if it is a 4-bit input, 4-bit shift register, so that whatever are the 4 bits that will come serially. Okay, so and it will be available at the output terminals in a parallel way. Okay, so that means there will be certain time required to load all the data. Okay, and then only it will be come out. Okay, so that means at each of the clock cycle data will be shifted. Okay, and after that uh, it is it will be transferred at the output terminal. So if it is a 4-bit shift register, then 4 clock cycles are required to get the output. In parallel out shift register, we require just a single uh, clock cycle, but here we require 4 clock cycles. So now we are going to discuss about that shift register. So we are going to write a VHDL code for that. So let us write it in the same project. So my screen is visible to all.
Yes, ma'am.
So now we are going to have a new shift resource. So I'll add that resource here. So first we are going to add the VHDL module. So we'll give the name to this, that is a SIPO. Okay. So here I'll just add one more thing, that is a shift register SIPO underscore SR, that means serial in parallel out shift register. Okay. Click on next and then you will get here inputs. Okay. So for this, what will be the inputs now for serial in parallel out shift register?
Only one input that is D and outputs are Q1, Q2, Q0, Q1, Q2 and Q3.
Yes. So only one input, that is a D, and clock signal. Okay. At the same time, clock signal will be required, and then we will add one more input signal, that is a clear. Okay. So that means to clear whatever is the data present. That so for that purpose we will have add one and then output, that is a, as we are going to have this shift register 4 bits, so output will be of 4 bits. So let us have this as a bus. So I'll say Q, that is a bus, and it is a of 3 down to 0. Okay, so that means it is a 4 bit. And now I'll take this as an in out because I want to use this output bit as an input also, and that is why I will use this direction as an in out. Okay, so that means I'm going to add this as a, wait a minute. So this is a entity, that means the port declaration part that we are going to do here. So we have output, that is a inout, because we want to use the same output as an input also, and that is why we have used the direction as an inout. So that means it will work in a both the direction. And then input, that is a D, clock, this is a serial input, D, then clock signal and clear signal. Okay, so these are the ports in this entity. Okay, so click on next, then you will find here a summary of this project, and then click on the finish. And then here you will find the VHDL code. Okay, so here library declaration part, as usual you can see here. Then after that, here it is a entity declaration part. So as we have here in these input ports, that is a D, clock and clear, and then output port, that is the in-out port Q. Okay, so this is the entity declaration part, then end of the entity declaration, and then we have architecture of this parallel out shift register. Okay, so here as we want to uh, process this signal, in a sequential manner, so we will write a process here, to declare process, to process, and the sensitivity parameter for this is the clock. So depending on the variation or changes in the clock, the statements in this process that are going to be executed. So let us start with the beginning of this process, and then here, now what we want, if clear signal is equal to 1, then we want all the output bits that to be 0. Okay, so for that I'll write a statement, that is if clear is equal to 1, then Q is assigned to 0, 0, 0. Okay, so that means what we are doing here, whenever clear is equal to 1, that time we are resetting the shift register, we are making all the output bits of the shift register that is equal to 0. Okay, else what we want to do, else if clock event, that means if there is any change in the edge of this clock signal and clock is equal to 1, then okay. Now what we are going to do, what we want actually, whenever there is a clock signal, okay, so rising edge, at each of the rising edge of the clock, whatever is the bit which is available at the input port, okay, that we want to be the bit at least significant bit of the output. Okay, that means at Q0. Okay, and then we want all the bits that earlier bits that to be shifted. Okay, so that means what we want, whatever was the earlier Q2 that to be Q3, whatever was earlier Q1 that to be Q2, and Q0 that we want to be as a Q1. Okay, so in that way we want to shift that. Then त्याप्रमाणे तुमचं shift होणार आहे, तुमचं shift register मधला data. So what we are going to do,
Excuse me,
Q0
ma'am.
bit ला आपण, yes,
Ma'am, clear is equal to 1. इथे then T च्या जागी R झालं.
Where? Oh, okay. Thank you. Okay. So then what we want? Q3 3 down to 1 is assigned to Q2 down to 0. That means now here Q3, whenever there is a clock event and clock is equal to 1, then Q3 will be equal to Q2, Q2 will be equal to Q1, and Q1 will be equal to Q0. And what we want? Q0 that is equal to D, that is a serial input. Okay. And then end of this if statement, then end of this process, and end of the architecture. So that, okay. So this is the VHDL code for this serial and parallel out shift register. Now look at this code and tell me if there is any error in this code. Radhika, is there any error in this code? Okay, tell me about the syntax error.
Ma'am, Q is assigned to 0, the semicolon is right.
Yes, okay. So here there should be semicolon at this statement. Otherwise, it would have a syntax error there. Okay. So here, this is now code for serial in parallel out shift register. So let us save this. Click on this so that we can check the syntax. So our syntax that has been completed, checked, that has been completed successfully. And so now let us proceed for writing test bench for this code. Okay. So let us add a new source. Now as we want to write a test bench, so let us select a source type, that is a VHDL test bench, and give the name to this test bench as a serial in parallel out, so SRTO underscore SR underscore TB. So this is the file name that we are going to give this to this test bench. This test bench TB that will represent as a, this is the test bench for certain VHDL code. Okay. So that is why we are taking this extension to this name. Okay. So click on the next, and now we want to associate this source with SRTO underscore SR. That means with this VHDL code, and that is why click on this. Otherwise, if you click on this and then click on the next, then whatever is the test bench that will get associated with this source, and that is, then it will be you will found that whatever is the component that is instantiated or that is declared in your code is related with the parallel in parallel out shift register. And though if you are thinking that whatever I am going to write VHDL code that is related with serial in parallel out, but as it that code is associated with PICO, that is a parallel in parallel out shift register, it will show result in that way only. Okay. So whenever you are going to associate your source with a particular source, then you have to take care that you are selecting a proper source or and correct source. Okay, so here we are going to select this SRPO underscore SR source, click on the next and click on finish. Then here you will find a text bench code. Okay. So here in this text bench you will find library declaration part. Then after that there is an entity, but here you can see that this entity is the empty entity. There is no any port declaration part there. Okay, because actually in this test bench we are declaring certain component and whatever are the ports of this uh, statement, so that will be mapped with the ports of the component. Okay, so here no separate port declaration part will be there. So after that in a architecture you can see the component declaration part. So the serial in parallel out shift register that is declared in this architecture. After that there is a input signals. Okay, so that you can find here. Now these are the initial values for this input. So now here initial value for D input, that is 0, clock that is also 0, and clear is also 0, that is the by default value of these signals. But actually what we want, when this unit that is a component that should be resetted whenever clear is equal to 1, and that is why we will make initial value of this clear as equal to 1. Okay, that means what will happen now, initially your shift register will be set as 0 value. Okay, so that means it will get resetted as the clear is equal to 1, also clock is equal to 0. So in that way, this component will be resetted. Okay, so here this is the clear signal which we have made equal to 1. Okay, then after that this is the output signal. Okay, so which is a bidirectional actually. So here this is the signal to which is the std underscore logic underscore vector, which is a 3 down to 0, and after that we have declared one constant, that is the clock period, which is having the time, that is a 10 nanoseconds. That means this clock period which is in terms stop time and it is of 10 nanoseconds. Then after that there is a port mapping of this ports of test bench component and the actual component that we have instantiated, and then clock process that will be there. Okay, so clock process, in that we are making on time and off time that are of equal size and that are of 5 nanoseconds. Okay, and then after that there will be a stimulus process. So stimulus process, in that we are going to now declare input. Okay, so here we are going to wait for 10 nanoseconds only, and after that we'll make clear equal to 0. And then let us make D that is equal to 1. Okay, so we'll assign value D that is equal to 0. Then after that we are going to wait for 10 nanoseconds, or let us wait for 2. Okay, initially I'll keep this as this much only. Okay, then I'll just copy this so that it will save my typing time. I'll make this as a 0. Okay, after that so here I have assigned this values as a 1010. Okay, so that means here now 1010, that will be the serial input. Okay, and now after that we are going to wait for 10 nanoseconds and wait for clock period multiplied by 10. Okay, so that much. Okay, I'll make it as a 5 only. Okay, then we are going to wait, and then end of this process and end of the actual architecture. Okay, so let us save this. Okay, then click on simulation here. So in a view, click on simulation. Now right now we were doing implementation. Now we want to simulate this. So click on simulation and then select a proper test bench. So we are going to simulate this SRTO underscore SR underscore TD, that test bench. So click on that and then click on behavioral check center. So this has been completed successfully. So let us now simulate this behavioral. Now here initially you can see that initially our input was 0000. Okay, so here uh, as the clear was initially as the clear was 1 for first 10 nanoseconds, so output was 0000. Though d is equal to 0, so that means output is going to be 0 only, but as clear is equal to 1 again, so output that will be equal to 0. Now this will remain till there is a clock event. Okay. Now though here uh, clock clear becomes 0, but and, and d also becomes 1, but still there is a rising edge of the clock and clock becomes 1. Output will not change. So at that instance now whatever is the value of d, that will be available at Q0. Okay. So here now you can see output is 0001. Okay. Now in the again for the next clock signal, whatever is the value of d, that will be shifted now. So here output will be now 0010. Then in the third clock signal, output becomes now 0101, and at the fourth clock signal, it becomes 1010. Okay. Now here actually we have not used a loading there. Okay, actually we need to use a load signal also, because first of all whenever we are considering a serial in parallel out shift register, it will just load and then it will read output. Okay, but just for the simplicity we have used this much code only. So at each of the clock signal you will get certain output. Okay, so here now at the fourth clock signal actually you are getting whatever is the correct output, so that is the 1010. Okay. And then after that, as we have not initialized any input, so d will become a 0, and then depending on that you will get output. Okay. So this is a serial in parallel out shift register. Okay. So here you can see that whatever is your input, how it is serially getting shifted, and then it is a parallelly out. Okay. So that means at each of the outputs you are getting this output. Okay. So this is a serial in parallel out shift register. Now, if anyone is having any doubt about this, please let me know. Any doubt?
No doubt, ma'am.
Okay. So this is a serial in parallel out shift register. Now in your syllabus, only these are mentioned, but still we are going to discuss about one more type, that is a serial in serial out shift register. Okay. So let us discuss about that shift register. So, now tell me, what is mean by serial in serial out shift register?
In this device, we apply the input serially and we get the output serially.
Okay, so that means uh, at the first flip flop we are giving the input, and at the last flip flop we are taking the output. So it is at each of the clock signal data will be come out. Okay, so that means in a serial manner it will come out. Okay, and at fourth clock signal we will get complete data, that is a 4-bit data. Okay. So that is a serial in, serial out shift register. So now let us write a VHDL code for this. So let us do implementation, add a new source, and then select a source type, that is a VHDL model. Okay. Uh, give the name to this as a SRSO underscore SR. Okay. And then click on next. Now, what will be the port for serial in, serial out shift register?
Q, D, and clock.
Yes. Uh, Input. Okay. So I'll say this as a D.
D is input, clock is also input, and
Clock
Q
is
is
also
output.
input and Q is a output. Okay. So only these will be the ports in this entity. So click on this and click on finish. Okay. So now here we are going to write a architecture. Okay. So as you can see here, library declaration part, then entity depending on the ports that you have selected, and then after that there is an architecture. Okay. So here in the architecture we are going to select one signal. Okay. So temporary signal declaring we have one signal, that is a signal TMP, and it is the signal that is a 4-bit. Okay. So std underscore logic underscore vector. Okay. And the range that we are going to select for this is a 4-bit. So 3 down to 0. Okay. Then we are going to begin with the architecture. So this is the code declaration that we are going to do for this architecture only. Okay. After that we are going to write a process, okay, where the sensitivity parameter for this is the clock. Then begin for this process, and after that what we want, if there is any clock event and clock equal to 1, then now here we are going to use a for loop. Okay. So till now we have not used this for loop anymore, but now in this we are going to use a for loop. So here for I, that is the index, in the range of, so here in range that we are going to have is a 0 to 2. Now why we are going to select this, that we will discuss afterwards. So this is the range for this for loop, and then the keyword, that is a 2. Okay. So this is the syntax for loop, that the keyword for, then index, and then in, this is the keyword, and then range of that. Okay. And then there is a keyword, that is a loop. Okay. So here after that TMP, that is a temporary signal that we have used, I plus 1, that is assigned to the value TMPI. Okay. End of this for loop. then TMP0, that is equal to D. And then end of this if statement, end of the process, and after that we are going to assign a Q value that is equal to temp 3 and then end of the architecture. Okay. So this is the code for the serial in, serial out shift register. So here now what is going to happen? Your data will be in a serial manner and it will be out in a also serial manner. Okay. So here this architecture. In that architecture, we have assigned or we have declared one temporary signal, which is a vector, which is of a 4-bit. Okay. And then what we are doing? We are using at each of the rising edge of the clock signal, we are going to assign TMPI plus 1, that is equal to TMPI. Okay. So that means in the for when I is equal to 0. Okay. So this loop we are going to iterate for the 3 times. Okay. Okay. And then uh, we will have TMPI plus 1 that is equal to TMPI, then TMP0 that we are going to assign as the value of D. Okay. So that means this we are going to do for 3 times, and in the after that we are going to assign TMP 0 value, that is of whatever is the input. Okay. And then end of the process, if loop, then end of the process, and whatever is the value of Q that we are going to have as a TMP. Okay. So this is the VHDL code for serial in, serial out shift register. Okay. Let us save this code. There are errors. So let us find out this error. So Q. Okay. So this bracket is not closed. So okay. Then end of each. Okay, so first let me save this. So at this there is a error. Can anybody discuss what is the error?
Now look for loop method.
Yes. Hello.
मॅम टेंथ असाइन केलं तिथे सेमिकोलॉन राहिले लूपमध्ये.
Okay. Actually, I'm not getting right now what is the error, but I will just find out this error, uh, and then we will discuss about this in the next session. Okay. So once again, we will discuss about this, and then we will do simulation of this code. But for right now, then we will. But you can check for this what is the error, and you can tell me so that we will modify this code. Okay. Uh,
मॅम फॉर लूपमध्ये जिथे आपण टेम्प असाइन केलंय ना
hmm.
मॅम तिथे सेमिकोलॉन एक राहिलाय.
Oh. Yes. Okay. So that was the error. And then thank you, Prajakta. Um, so sometimes this happens. This was a very small mistake, but I was not able to find out that. Okay. So now let us fix syntax for this. So the syntax has been checked successfully, and therefore we will write now a test bench code for this. So add test bench, and then so underscore tb. Click on next. Okay, we'll select this VHDL code and click on finish. So here now we are going to assign a similar. So let us have for the first time, let us make b equal to 1. Okay, wait for some time. Again, there should be a semicolon. So let us copy this code and paste here. I'll make this as a 0. Then after that again I'll paste it and keep it as a 1. And then I'll make it as a keep it as a 1. Okay, so that means we are giving the input that is a 1011. Okay. not wait for 10, but instead of that, I will have just 5 clock cycles. Save this, click on simulation and select a proper test bench. Here, click enter. Okay, so it has been completed successfully. So let us go for simulation. Okay, actually, here at this cycle, output should become as a 1, then 0, 1, 1. Okay, so in that way, we should get output. Here again, there is certain error. So let us debug this afterwards. Okay, so for today, we will stop here as there is error in the output. I will check it out, and then in tomorrow's session, we will discuss again about this. Okay, so now stop the recording.